our input voltage has to be slightly greater than the output voltage in linear mode power supplies, and because efficiency is low, so we cannot use it for high power applications, right? So this, if voltage is less than 20 volts, then it efficiency is very low, 30 to 60% only. So that is the reason that we went for high power supply, switch mode power supplies or PWM converters. In PWM converters, what we have seen that our converter works in either saturation region, this region when it is on, or cutoff region, this region when this is off. So due to which in cutoff region, the voltage is almost zero. In saturation region, voltage across the device is almost zero. Current is only there, and in cutoff region, the current through the device is almost zero, and there is only voltage. So the power losses in this is expected to be very less, right? And we have seen that the efficiency improves quite significantly. Ideally, it is 100%, but if we consider some of the losses in switch, inductor, capacitors, then this efficiency is still good, right? And if we see that from the at this point we have already discussed that it is why efficient, because transistor operates in cutoff region or saturation region. Also here in linear mode power supply, what we have seen, if you give one input, then we can get one output only. But in PWM converter, like further we divide it into two parts. One is non-isolated, another is isolated, right? So in isolated version of this PWM converter, we can have multiple output as well. Multiple output as well. Nowadays, there are topologies for non-isolated also, where you have single input, dual output, single input, multi-output, pseudo converters, dual input, single output, DSO converters, or MIMO, multi-input, multi-output, SIDO, single input, dual output, DSO, dual input, single output, or you can say MIMO in general, multi input, multi output. So why these converters are useful? Because you have nowadays, we have this DC microgrid concept, or this mm, distributed energy resources are there. So if you have one battery is there, let's say, another is with you solar PV, solar PV. So what normally you do, you use one converter for solar PV, it boosts it. So you use some boost converter, it will give some voltage. Then this is a bidirectional converter, you attach with the battery, okay, bidirectional converter. Then this will give power to the load, and here is our load. Now what you can do, if you integrate these two converters together, then it becomes single converter. We call it to be integrated multi-port converter. Then you have now two inputs. One is solar PV, one is battery. Now depending upon which input is available over here, you have one output. So it what dual input, single output. And when let's say battery itself is getting charged, if solar PV is more, then what is happening? Battery itself becomes a load. Now solar PV is the only input. So this converter function says single input, dual output, single input, dual output, right? So that is the way we need this single input, multiple output inverters, or you can say simply multiple output converters we need. So this is provided in case of switching regulators, which are not there in linear power supply. And if we increase the frequency, then the size and cost becomes smaller, right? So that we have seen in throughout this FDP. And further, because power losses are less, so heat dissipation will be less. so heat sink requirement is less. That's why these converters are also uh, they are compact. But they also carry some disadvantages. That disadvantages here lies here, that why still efficiency is not near to 100%. So what is the reason? So we have seen that these converters are, if when they are working on high current levels, then we have conduction losses, we have switching losses. So make it compact and the size. But the another problem with increasing switching frequency is that switching losses gets increased. Switching losses gets increased. And also this EMI, electromagnetic interference. I'll discuss what is this EMI, electromagnetic interferences. That also gets increased. That's also gets increased. What is this EMI? EMI is just, we can define, they are high. Where should I define? So these EMIs are called electromagnetic interference. So what happens when this converter is operating over here? Now this converter, some inductor current will be there, right? And when this inductor current is like, or this switch is operating, then there will be some switching transient across this, which we call di by dt and dv by dt, right? Now these dv by dt and di by dt will cause certain fields, electromagnetic fields, and now these electromagnetic fields will affect. There are, let's say, some more equipment over here, then these fields will affect this equipment. Similarly, if there are some other equipment nearby this, so their fields will affect this equipment. That's why this electromagnetic interference will take place, and it impairs the performance of our converter and nearby devices, right? So this is due to this di by dt and dv by dt. If this di by dt and dv by dt can be suppressed anyhow, then we will be able to reduce the EMI. So that is also an issue if you are increasing frequency, because if you increase the frequency, there will be more time, number of times in a fixed time, that these on and off instance will occur, right? So it's a like, it's a set of you have to make. It's not like that any frequency in megahertz I can keep just to reduce the size. If you will be able to reduce the size, but if converter performance is not sufficient, not satisfactory, then what is the use? So in order to resolve these disadvantages, we go for some other topologies, right? So I think, yeah, we have discussed all these disadvantages. Go for other topologies, and those topologies are called soft switching resonant converters. Soft switching resonant converters. So what is the purpose? The purpose is to reduce the switching losses, and the purpose is basically to reduce this di by dt, dv by dt. If it can be, okay, if it can be reduced anyhow, then we will be able to operate these converters at higher frequency. Now, before going to this word soft switching, what does it mean? Let us see what is the hard switching. Hard switching. So when we were seeing the characteristics of ideal switch and non-ideal switch, that time we have seen these things. That in hard switching, what happens? Ideally, if you say when switch is turned on, let's say this is the current, When switch is turned on, your current suddenly jumps to this, right? And your voltage jumps from here to here, right? At this instant, switch is on. This instant, switch is on. So this is a voltage going to some value. This is sorry, this is current going to certain value, and this is going to some uh, zero value, right? Now, if you see, I say this to be ideal. Zero ideally will be infinite. Dp by dt will be infinite because the time interval is zero and there is some del I, there is some del V. Similarly, this is when on. Similarly, when this is off, then also, if I talk about current, then current will reduce to zero. It was having certain value, now it will reduce to zero. Okay, this is zero level, let's say. Now voltage also, when current was having some value, voltage was zero. Now when current becomes zero, then voltage will be set to some value. Here also, just a minute, there is some issue here in this touch screen. I have to. You give me 2-3 minutes, it will take. I have to change my this system. Just give me 2-3 minutes. I'll join. System. I'm back in 2-3 minutes. I say. Is it visible? Is this slide visible now? Neha, is slide visible?
Yes, sir.
Okay. Okay. So we were discussing over here. Sorry, actually, some issues had happened here, so I have to. Okay, so our purpose was to change the to reduce the dv by dt and di by dt. So in off case also we have seen that here di by dt and dv by dt that's are quite high. Now when we talked about non-ideal switches, so in this case, though your efficiency is 100% and your you say but dv by dt and di by dt that is very high. In case of non-ideal switch, what we have seen in case of non-ideal switch even that this current was increasing and it was taking some time. Similarly, the voltage was decreasing and it was taking certain time. During this period, we had certain losses. During this period, we had certain losses, and these losses similarly at when it is happening like this, here also we had losses. We discussed it, right? We discussed, and these losses were called switching losses. So even in case of non-ideal switches, maybe this transition is bit smooth, but this is not very smooth also. This time period is also very small. So still this dv by dt and di by dt do exist over there also, right? And apart from that, losses come into picture, right? So if you are doing switching frequency to be very, you are keeping switching frequency to be very high. It does mean that again and again you are repeating this process. So multiple time you repeat this process, then what will happen? This losses will increase and the EMI phenomena which is happening due to this di by dt, that will also repeat, that will also increase, right? And we know that this p average in case of non-ideality, this was v of I on upon ts, which is into frequency, into t on plus t off. If you remember, we discussed this formula, we derived these formulas in I on v on upon ts minus t off minus t on. Okay, so now this formula suggests that how to change colors. Okay, so I don't know what is happening. Here, this switching loss is proportional to the switching loss. P switching loss is proportional to Fs. This is proportional to Fs. Now, when this is proportional to Fs, it means I can not increase switching frequency to be very high. And here it is not dependent on switching frequency, but V1 and I1 is high. So basically, this conduction losses, whatever it is, that will be there. That cannot, that cannot be reduced or will not. Our aim is not to reduce that. Our aim is to reduce switching losses and dB by dt and di by dt. That is the our aim. So in switching frequency, in soft switching, what happens and what is the soft switching? If I say soft switching, I define, then soft switching is basically the technique by which in at least one or more switches, one or more switches, in one or more switches. If you in maybe it may happen in inverters, it may happen in DC to DC converters both. If you can at least reduce or eliminate either the turn on losses or turn off losses or both, either turn on losses or turn off losses or both, then we call such converter to be soft switching converter. Right? So basically how it is happening, it is happening through process of creating resonance in the circuit itself. So your normal conventional buck converter circuit is there. Now you modify the topology and you insert some additional inductance and capacitance, and due to which resonance occurs. And when resonance occurs, then is whenever there is a current is zero or voltage is zero, that time you will make the other switch on or off depending upon the circuit conditions. So that time you can make this switching losses to be zero. So those converters are called resonant converters. Soft switching resonant converters. Now in soft switching resonant converters, we use full resonance phenomena. So in this approach, a full resonance phenomena is created within the converter by using different combinations, series parallel combinations of inductors and capacitors. So that is the one kind of topology, resonant converter. The other kind of topology which we use is called quasi-resonant converters. So what is this quasi-resonant converters? In this also we create the resonance, but we take the conventional, why this feature and all not coming. Screen drive, smart select, create node. What is this create node? Is it possible? No. No, same. Okay, so what is this quasi-resonant converter? In quasi-resonant converter, we use the conventional DC to DC converter. Right? PWM converter itself. In this PWM converter, we take PWM switch. Right? And in that PWM switch, we use some inductor and capacitor, and we introduce resonance in PWM switch itself. And then this PWM switch is inserted. We will see some of the topologies. Then we insert this PWM switch or we replace this PWM switch by PWM resonant switch, right? And remaining circuit is kept as it is. Then we call such converter to be quasi-resonant converters. Quasi-resonant converters. So basically, in quasi-resonant converter, I repeat, what we do, we use conventional PWM converter and replace the switch with a resonant switch, right? Resonant switch. What we are calling to be resonant switch? Normally a PWM switch in which some resonant components L and C are used, and then this circuit accomplishes the task of loss elimination, right? So here what is happening? It's not fully resonant. Now the nature of switch is nature of the switch is PWM, but resonance is also occurring for short interval in that switch. So it is called quasi-resonant converters. And these converters we will be discussing. So what is basically being done in this uh, soft switching converters, DC to DC? Which can be done is in between, right? So what is done here? First we convert the DC into AC, high frequency AC. Then this AC is given to our resonant stage, and which further converts it into DC. So why? What is the need of converting this into AC? Because in AC, what happens here? These switches are there, so switches have natural commutation, right? They will naturally reach to zero, right? And like whatever we have seen here, we have to force it to become zero, right? We have to force this current to become zero. But in AC circuits, this current is naturally zero. Voltage is naturally zero. That's why it's alternating. It will reach peak and it has to come zero. And we will track that point of zero current or zero voltage level. And accordingly, we make switch on and switch off. So that's why we use it in two stages. And resonant tank is used here. Resonant stage or resonant tank. Resonant tank is basically LC combinations. So that is used here to provide that particular time, that particular this zero crossing, right? So the resonant tank, which serves as an energy buffer between the input and the output, is normally synthesized by using a lossless frequency selective network. The purpose of that network is to regulate the energy flow from the source to load. And this resonant stage is composed of L and C, which is very small in compared to the inductor and capacitor of the switches, right? And due to which, and they are ideal in nature, so this resonant stage itself does not create any issue to efficiency. Otherwise, people may say that you are using more components. So further, they will reduce the efficiency, but this will not happen because nature is L and C, which are normally ideal or near to ideal. So that's the comparison which we have already done. Just I read these slides. PWM converter. The switching of semiconductor devices normally occurs at high current levels. Therefore, when switching at high frequency, these converters are associated with high power dissipation in their switching devices. Further, the PWM converters suffer from EMI, electromagnetic interference, by high frequency harmonic components associated with their quasi square switching current or voltage waveforms. In the resonant techniques, the switching losses in the semiconductor devices are avoided due to the fact that the current through or voltage across the switching devices at the switching point is equal to or near zero. That's what natural commutation I told. Compared to the PWM converter, the resonant converter shows a promise of achieving the design of small size and weight converters. That's the target. Another advantage of resonant converters over PWM converter is decrease of harmonic content in the converter voltage and current waveforms. So this is comparison of that how this hard switching and soft switching work, right? So in hard switching, this is like a switching strategies we call it to be. In hard switching, this current and voltages, they are suddenly jump, right? They are suddenly jump. But if you use, as soon as you make it to be on, then it was having this value V of, then it will suddenly, when you make it turn on, it suddenly goes to zero in this fashion, right? But if you use numbers, then in existing, in existing even existing PWM converter also, if you use snubbers, then this is the purpose of using snubber is just to suppress the DI dt. So you know that when this switch is there, what we do normally in normal converters, we use inductor for reducing this DI dt, and we use one capacitor in parallel to this switch in order to mitigate this dV dt. That is being done in normal converters. But in soft switching, what happens in soft switching? This trajectory of the switching, when you make it off, right? Then it does not go directly to zero. It goes smoothly, right? It goes smoothly. So that's the ZVS turn on. What is ZVS, ZCS? We will see. So now there is two techniques. There is for this we have discussed switching loss in power devices. This we discussed just when this is turn off at this point. So before turning on, this current was there. It will smoothly go on. When turn on, then voltage will build up. During this period, this power loss will occur. During turn on, current was zero. It is slightly increasing and then settles. Voltage slightly decreasing, then settles. Then this is the power loss, right? So this is turn off and turn on losses. Now our aim is to mitigate that. So there are two ways to do this. There are two ways to do it. One is called zero voltage switching, ZVS, and ZCS. ZCS. Zero. Two techniques are there. Zero voltage switching. Another is zero current switching. Zero voltage switching and zero current switching. So as the name suggests, this ZCS. First, let's say ZCS, zero current switching. It means the current through the switch should be zero. So this is basic. This is normally used in turning off the switch, or to turn off the switch or to turn off the switch. Now, if we want to turn off the switch, it means it is already on. So if it is on, then it is carrying some current ion and voltage is zero. So in normal case, as soon as you turn off it, then what happens? This current start decreasing, and at the same instant, this voltage starts increasing. And that is the only cause of, because this voltage and current, they are coming together at same time. They are coming together at same time. So this power loss occurs. But if something is happened such that, when current through the switch becomes zero, when current through the switch becomes zero, if current has become zero, after that, if this increases, this voltage, if I can do something like that, right? Then what will happen? This period current is there, but no voltage. So what will be the output? Power loss across the switch. Power loss in the switch, that is zero. Now here current has become zero, and it will be zero. And after that only voltage is building up. So during this period, what will happen? Power will be zero, right? So it results in zero power loss during this switching period when it is getting off. When it is getting off. Now you may say, okay, sir, then this period unnecessary will create a problem. It will be like this much time will be taken in turning off only, proper start of the converter, because whenever this proper voltage is built up, then I will say that it is turn off. Then again, the issue is that because now this power loss has become zero. So I can repeat this process multiple times, right? I can repeat this process multiple times. If I repeat it multiple times, it means I can increase the frequency. Now the effect of increasing frequency is not affecting our power loss, right? So what we do, we can increase now frequency, and accordingly, when you increase the frequency, this period can be controlled by selecting proper resonant converters. And this condition, which will be created by using some additional components, so that the voltage will be built up or will start building up across the switch when current becomes zero. Right. So that's the fundamental phenomena of ZCS. How does ZCS works? How does ZCS works? Now, so in the, how can we define this ZCS? This is the turn off process. This is the turn off process, or you can say this the turn off process starts. You can say the turn off process starts in ZCS. In ZCS, the turn off process starts when current through the switch is zero. When the current through the switch is zero. Now, in the same fashion, what is the ZVS? The ZVS is zero voltage switching. Now you see here, it is basically used in turning on of the switch. Turn on. It is used to turn on the switch. So when switch is turned off, there is some voltage across this, and the current through the switch is zero. Current through the switch is zero. Now power is zero. But the problem starts when you make the switch on at this point. As soon as you make the current, the switch on, then what will happen? Current will build up through the switch, and it will take certain time. But same time only, this starts. Same time only, this voltage goes down and it becomes zero. And due to this, loss is occurring. But if anyhow I can do such things that once this voltage is zero, this voltage becomes zero, right? After that only I start current, right? After that only I start this current. Then this voltage is there, but current is not there, so power loss will be zero. Similarly here, current will be there, voltage will not be there, so power loss will be zero. So in this case also, I can keep this the losses during transition to be zero. Losses during this transition to be zero. You may say that, sir, can why to wait for this? The reason is that this is zero, right? This is already zero. We can ask this fellow to wait for some time, but this voltage is already high, right? This voltage is already high, so we cannot reduce it suddenly to zero. So we must wait for reducing it to zero as soon as possible, and after then we can start it, right? So this is called zero voltage switching. So we can define the zero voltage switching as the turn off, not turn off. I don't know how by this pencil. See, turn on starts when voltage across the switch is zero, right? So this is our, we are talking when about this voltage and current. So this is basically the current and voltage in this switch itself. Okay. So that's how we define the ZCS and ZV. Now let us see that how to use them. How to use them in circuits. So remember that we are talking about quasi-resonant converters. Quasi-resonant converter in which we will replace the switch. We will replace the switch along with its resonant switch. So what kind of resonant switch is being used? So first we are talking about zero switching topologies. So previously we have seen that this is used for turn off the device. Turn off the device. This is normally used for for turning off the device. Now this is our switch. This is our switch. So what we do in this case? What we do in this case? There are two type of switches: L type switch and M type switch. And within that, one is half wave implementation, one is full wave implementation. One is half wave implementation, one is full wave implementation. So depending on the inductor capacitor arrangement, there are two possible type of resonant switch. Inductor L is connected in series with the switch to achieve ZCS, right? So this inductor is connected. Basically, this inductor is connected in series, and then this capacitor is used in parallel, right? The inductor limits the di by dt of L and C constitute resonant circuit. So because this L, we are here trying to reduce this L di by dt. It's a turn off process. Na? So it means current is reducing. Current is reducing means we are controlling di by dt, right? So di by dt. That's why we have to connect an inductor. But inductor itself not create a resonance. So we have to use one capacitor at least. That's why one capacitor is used here along with this. So this will be the configuration. Now this is L type. But if you want to make it, let's say unidirectional only, then we connect a diode in this. Then we connect a diode along with this. And if you want to make it a bidirectional, then we also connect a diode in anti-parallel to switch. So this diode will make sure that current will not be flown through this MOSFET, and this diode will make ensure that current will flow through the switch if there is any reverse current flow. So that's like unidirectional and bidirectional. In M type also, like in this L type switch, we connected this capacitor over here. In this, we connect this capacitor across this combination. If you want to make it unidirectional, connect a diode. If you want to make it bidirectional, connect a diode in anti-parallel, then capacitor will be there. So that is how these topologies means. Now this is for switch, right? So once you that particular converter. Now we need to replace this with that switch. Maybe it's a buck converter, boost converter, buck boost converter, or any converter with this arrangement. So this will, rest of the circuit we are not worried about. What is the rest of the circuit? Rest of the circuit can be anything. We just need to replace the switch, because we are creating a quasi-resonant phenomena. Okay, so let us discuss how to use. So this is basic our conventional buck converter, boost converter, and buck boost converter. So we can have ZCS buck converter, ZCS boost converter, we can have ZCS buck boost converter, right? So when we are like let's say now we will go for designing a ZCS converter for buck, right? Similarly, we can have it for boost. So let us for buck. So before that, I tell you that how our circuit becomes. This will be our circuit. So originally what we were having, originally we were not, original circuit was like this only. If I throw it somewhere here. We denote it to be C node, L node in this particular case, right? This is our original circuit. Now we are not disturbing this circuit. We are not disturbing this circuit. We are just replacing this switch, and we have just seen that this switch can be replaced with this L type switch, right? So that switch is replaced, and the remaining circuit between this point and this point is same. Sorry, from here. So this circuit remains same. Now is our this is our ZCS buck converter. This is our ZCS buck converter. Now, in order to simplify this, actual will be like this only. Actual will be this circuit. But in order to simplify this, we do some assumptions. What assumptions we do? That we have seen in buck converter analysis also, that this is our load current and this is inductor current, right? This is our capacitor, this is our capacitor voltage, and this is our capacitor load voltage. In a steady state, the average current through this capacitor is zero. And this load current and this inductor current both are almost same. So whatever current is being flown here, that we can assume to be constant, right? So that's what we have replaced this entire configuration, this entire thing to be I node, to be I node, right? So our simplified circuit becomes this one. Our simplified circuit becomes this one. Apart from that, what are the other assumptions that uh, what are the other assumptions? This L node, R node, L node, C node, L node, C node are very, very large in compared to this resonant tank. The L and C, this we call to be resonant tank, are very, very large in comparison to this L and C of resonant component, resonant tank. Okay, and that is the first assumption. Second assumptions, we have assumed that this filter L naught C R, this is called output filter, output filter. So that is replaced as a constant current. That is replaced as a constant current source I node. That is our another assumption. And this is not required here, but we will see in boost converter case. If this L is not there, then we consider this C node and R node, parallel combination of R node, C node, right? So this can be assumed as constant voltage source. So depending upon whether this L, C, R combination is there, or instead of L there is a diode, then we consider R naught C naught to be constant voltage source. And definitely this is for assumption simplification purpose only. This is just for simplification purpose only. And all the switching devices, another thing is that all switching devices, diodes, and energy storage element circuits components, energy storage components, basically L and C, they are ideal. Hmm? Which is replaced by resonant type circuit to obtain a quasi-resonant buck converter. So in this case, there will be four mode of operation. In this case, there will be four mode of operation. Let us see what are the different mode of operation. Now we will examine this circuit. So remember that which circuit we were having. This capacitor is there, this diode is there, then this. So we will be examining this circuit now. This is the mode one. Right? So what we want to turn off the switch. It means when we want to turn off the switch, then what is the current through the switch before that? Zero. Before that current is zero. And this is the instant at which we want to, we have given instructions to turn on the switch, right? So switch is turned on. So first point is that switch is turned on at t equal to 0, right? So before that, what is the initial condition? For that, what is the initial conditions? At t equal to 0 plus, what is the initial conditions? So this is our circuit. This is our circuit. So when this switch is turned on, just before that, what was happening? This diode was conducting. This diode was conducting. So when diode was conducting, then what is the voltage across the capacitor? So at 0 plus, what is the capacitor voltage? 0. And because the switch was off, it is just turned on. So definitely inductor current will be 0. Inductor current will be 0. So we can see here inductor current, this is inductor current, this is 0. And this is capacitor voltage, which is also 0. Now in mode 1, we have turned on the switch. So this will be the equivalent circuit. Switch is turned on. Remember the original circuit, the switch is turned on, inductor is there, diode is already on, due to which capacitor is shorted. So capacitor is not shown here, and this is the current which is flowing to load through original inductor. You can say original inductor, L node. Now, how will be the equations? How will be the equations? So if I write equations across this VL, then what is this VL? L di by dt, L di by dt, right? So from here I can find IL, which is V, and this dIL by dt is equal to V in. So from here IL is equal to V in upon L into T plus initial current IL0, which is 0 in this case. So this equation becomes V in upon L into T. Now let's say this is equation number 2. Now here what this equation shows that inductor current is increasing linearly with the slope V in upon L. So inductor current is increasing like this. It will keep on increasing, but up to what point? Up to what point? So what is this current? I node. What is this current? I node. And when this mode started, before that, what was the current through this? I node, right? Now this mode has started. This is constant. This is constant. This current has started to increase with this law. It means summation of this IL plus this ID. That should be I node. Summation of IL plus ID. That should be I node. Correct? Now, because IL has started to build up, it means ID should go down. ID should go down. If I say this ID should go down like this, and when ID becomes 0, then the whole current I node will come through this inductor itself, right? It means when this mode starts, when this mode ends, when this diode current becomes 0, and when this diode current will become 0, when this inductor current becomes I node, it means if this IL becomes I node, at that time T equal to T1, this mode ends, right? This mode ends. So from here, I can get T1 is equal to Li node upon V in. Li node upon V in. So that is first end of first mode, right? So our current has reached here at the mode of at the end of mode 1. And what about the capacitor? Our capacitor is still 0. Why? Because this diode was on. Until unless this is on, capacitor voltage will remain 0. So up to this point, it is 0. Okay. Now what happens in mode 2? Let us see. So this is our mode 2. So now in mode 2, before proceeding to mode 2, let us write the initial condition for this mode 2. So this VCT1 is 0, right? And BC ILT1 off, because current now through this is 0, it cannot carry the negative current. Now this is the equivalent circuit for mode 2. Now in this circuit, what you will seeing that this capacitor has come into picture now. So diode is open circuited. Now there will be a resonance between L and C. This I node is constant. Switch remains on, because switch remains on only. We are using it for still switch is on, right? And what is our target? Our target is to turn off the switch. So we will turn off the switch when current through the switch will be 0. Yet current has not become 0 through the switch. So let us write the equation. So if I write the equation here in this loop, then what is that equation? VL is equal to L di by dt equal to V in minus BC. V in minus BC. And what is the second equation? Second equation you can write for you can write at this KCL. This is simply KVL. You can write one KCL. So KCL gives us IL equal to, or you can say IC. This let's say I define to be IC. then this IC is equal to IL minus I naught. That is our, let's say, another equation, 4 and 5. 4 and 5. Now we will simplify these two equations. So IC is basically C dVC by dt equal to IL minus I naught. Okay. So if I differentiate this 4, then what I get? L d2I upon dt2. Okay. V in is constant, so that will be 0 minus dVC by dt. If I put now, so this is equation 6. If I put 6 in 6, if I put this is, let's say, 5a. 5a. What I get? L d2I upon dt2 equal to 0 minus dVC upon dt. So minus 1 upon C IL minus I naught. Correct? So if I simplify this, I take C to be this side, this becomes LC d2I upon dt2. Then I take this term also this side plus IL minus I naught equal to 0. So I further divide this by LC, then it becomes d2I upon dt2 plus 1 upon LC into IL equal to I naught upon LC. Okay. So if I replace, let's say, omega node equal to 1 upon root LC, that means it becomes d2I upon dt2 plus omega node square IL plus equal omega node square I naught. So this is a second order differential equation in IL, where I naught is constant and omega naught is also constant, which is 1 upon root LC, right? So we have various different methods to solve this equation, and we can use those methods. So let us see, this is a second order equation. So its solution can be given as IL T equal to, its solution can be given IL T equal to A1 sine omega T minus T1. Omega naught, you can say omega naught T minus T1 plus A2 cos omega naught T minus T1 plus A3. Okay, so this is its generalized solution of a second. With us only this one equation, right? So how to find, and some other equation also. So how to find it? So let's apply the boundary conditions. Let's apply the boundary condition. So at t equal to t1, we know that IL T1 is, from this equation here, IL T1 is I naught. So let us put t equal to t1 here. So IL T1, that is I naught. If you put t equal to t1 in this, so it becomes A1 sine omega naught t1 minus t1, that is 0. If you put it here, then this is cos 0. Cos 0 is 1. So this is A2 plus A3. So this is the first equation which we get from here. A2 plus A3 equal to I naught. Now second equation. If I differentiate this equation with respect to t, then what I get? DIL by dt. That is then A1 omega naught cos omega naught t minus t1. Okay. Then I differentiate this also. So the differentiation of cos is sine. So it gives me minus A2 omega node sine omega node T minus T2, T minus sorry T1, and A3 differentiation is 0. So we can write it by simplifying A1 omega node cos omega node T minus T1 minus A2 omega node sine omega node T minus T1. So this is based upon the solution, है ना? This equation, main equation. Now, where do we have di upon dt? Let us look for these equations. This equation number 4. Equation number 4. So from equation number 4, we can write di by dt is equal to 1 upon L is equal to 1 upon L V in minus VCT, right? V in minus VCT. And now put T equal to T1 in this. So what does it give? Di by dt at T equal to T1. Let's say this equation is equation number 7. This is equation number 8. This is equation number 9. So di by dt at T equal to T1, if you put in, let's say 9 first, then it gives us equal to 1 by L V in minus VCT1, right? So what is VCT1? VCT1 is 0. So if you put it here, then this is V in upon L. And if you put same T equal to T1, if you see at equation number 8, then what is that? T equal to T1. A1, if you are putting T equal to T1 over here, then this gives me A1 cos omega naught. Cos of 0 is 1 minus A2 omega naught sine omega t. So this term becomes 0. T equal to T1, sine 0 is 0. So it is 0. It means A1 omega naught. So now this, let's say equation 10, this is equation 11. So this equation 10 and equation 11, both should be same, because one is coming from this assumed solution, another is coming from fundamentals. Both should be same. So if both are same, then I can equate this equation. And if I equate, then what I get? A1 equal to V in upon omega naught L. This is what I get A1. Okay, A1 is V in upon omega naught L. Equation 12, let's say. Now we had one equation, this one. Now we got A1. So step 3. Step 3 is that we can again differentiate this equation 9. Differentiate equation 9 once again. This is G2. Okay. So if I want to find the value of this at t equal to T1, then what is D2I? D2 at t equal to T1? 1 upon L minus dVC1 T, right? Minus d by dt VCT T1, right? Oh, I think I'm missing some coefficients. No, that is okay. Equation 9 is okay. Now d at T1 dVC itself is 0, so dVC by dt will be 0. It means this term should be 0 only. And now see same from equation 8. Equation 8. So if you differentiate equation 8, then this will be d2IL upon dt2 equal to minus A1 omega naught square sine omega naught T minus T1. We are differentiating this equation. minus A2 omega node square cos omega node T minus T1, right? So let us put T equal to T1 in this. Okay, so if you are putting T1 in this, so this term will be 0 and this term will be minus A2 omega node square, right? It means this omega A2 omega node square and this both should be same. So from here A2 comes out to be 0. So let us put A2 equal to 0 here. It means A3 comes out to be I node. So A2 is 0, A3 is I node, and A1 is V in upon omega node L. Let us put this in equation. This equation. Am I audible? Actually, power cut was there, so this internet and everything, got disconnected. Any one of you please respond? Am I audible? You can send a message. I'm audible, please let me know so I can continue. Okay, Neha got connected. Okay. So fine. So is the slides visible, Neha? Is the slides visible? कॉल करके बता दो. स्लाइड्स दिख रहा है क्या? ठीक है ना सर, मतलब कंटिन्यू. नहीं नहीं, वो मैं भी earlier he said now it's audible. I think I am speaking on this also tablet also audible na through tablet, and new slides also visible. Okay, fine, continue. Okay, sorry sir for interruption actually due to power failure. Okay, so what we got here now, this equation becomes the value of a1 is this, and value of a3 is this. So and value of a2 we just found that is 0. Hmm? So this equation becomes so this ILT, yeah, this one ILT, this ILT becomes now this A1, this is A3, A1 is here. So V in upon omega node L and sine omega node T minus T1, A2 is 0, so plus I node. So this is our equation, right? This is our equation which we have obtained after the getting solution of this particular mode. Now, what is the behavior of this equation? We will try to analyze, right? What is the behavior of this equation? So first, okay, we also try to get if we know the IL, if we know the IL, then we can get VC. We can get VC. How to get VC? Anyone can tell? From this equation, LdI by dt we can have, right? Then we can have this VC is equal to V in from here, V in minus L di by dt, right? So V in minus, what is this di by dt? This only. So V in omega node L into omega node cos of omega cos of omega node T minus T1 plus 0. So if you simplify that, then you will get VCT. VCT equal to V in 1 minus this L is already there. So this omega node will cancel out, L will cancel out. So V in 1 minus cos omega node T minus T1. So VCT and ILT we have obtained. Now let us see what is the nature of these two. So this ILT is I node, then there is a sinusoidal function. So here we see that this is IL. We were at this point at the starting of T1. Now from here it is increasing. How it is increasing? Sinusoidally it is increasing. So it increases sinusoidally, right? It is increasing sinusoidally. It is reaching to maximum. It is reaching to maximum. So it reaches maximum when this value is pi by 2. When this value is pi by 2, that because entire is pi, from here to here this is pi, so this is pi by 2, it is reaching at this point. So if this value is pi by 2, if you put it here, then cos pi by 2 is 0, so vct equal to v in, so your capacitor keep on increasing and it reaches to v in. So now capacitor voltage has reached here. After that, what happens? Current start decreasing because it's a sinusoidal function. So resonant tank is there like that. It start decreasing. So after pi, it becomes again to I node. So if you put pi over here, then what happens? Cos pi is -1. So 1 minus 1, 2 V in. So capacitor voltage reaches to 2 V in, right? And after that, it further decreases. Either further decreases, then it becomes 0. It becomes 0. And when it becomes 0, then there is certain voltage across the capacitor. There is certain voltage across the capacitor. So this mode ends when this inductor current becomes 0. This mode ends when this inductor current becomes 0. So if this inductor current is set to 0, then we can get at t equal to t2, this ILT to become 0. So we can get this time t2 minus t1 from here. So the del t2, the period for which this mode is functioning, that can be obtained. Now, what is the next? So the next mode, now what happens? Just look for this circuit. At the end of this mode, what we are getting? The current through this inductor has become 0 and there is voltage across this capacitor. Some voltage is there. Now, you know, diode was like this only. So this positive voltage is there. As long as this positive voltage is there across the diode, it will be reverse bias only. So we ensure that it is off only, right? And as soon as it was off at t equal to t1, after that continuously this voltage is positive only. This voltage positive only. So diode will remain off. Now inductor current has become 0. But remember, this inductor current is also the switch current in this mode. So inductor current has become 0, it means switch current has become 0. And this is the instant at which we say that we have achieved 0 current switching. It is the instant at which we have achieved 0 current. Now remember that ZC as 0 current switching we are using for turning off the MOSFET, So this is the right instant at which we should instruct the switch to be off, because after this our current will be 0 only. After that our current will be 0. So once it is off, now even if your the voltage across the switch keep on increasing, so where does it matter? Our current is 0, so losses will be 0, right? So this is the important point where ZCS is achieved. Okay. Now what happens in next next modes are simple only. Are you saving the current document? Process. Okay. So this mode is already clear. Now let us go to the mode 3. So just before the starting of mode 3, write the condition. Initial conditions of mode 2. So initial conditions of mode 2 were, this was having certain value VC2 to only. Inductor current has become 0. Now inductor current has become 0. It means the switch is now off. Capacitor is like this only, and capacitor voltage is on verge of decreasing. and this is the equivalent circuit. This is the equivalent circuit. Now in this case, what will happen? What is the circuit? If you write this equation, inductor current, so inductor current is 0 here, right? The only thing is that this, right? So if you are writing KCL at this point, so this is IC and this is I naught and this is IL which is 0, this is IL which is 0. So only thing is that IC will be equal to minus I naught, which is C dVc by dt equal to minus I naught, which is dVc by dt equal to minus I naught upon C, Vc equal to minus I naught upon C into T, plus initial condition, which is VCT2. So with this equation, this voltage will decrease. And this is, you can say this is a equation of a line. So from this point to this point, what will happen? This capacitor will be decreasing linearly. Capacitor voltage decreases linearly. Capacitor voltage decreases linearly. Now this capacitor voltage is decreasing linearly, and how long it will decrease? How long it will decrease? So what is VCT2? VCT2, if you see in the previous equation, VCT2 was V input 1 minus cos omega naught T minus T1. This was the equation. So at T equal to T2, this was the voltage. So this is the capacitor equation in this capacitor voltage equation in this particular mode. Okay, so at T3, this mode ends. This mode ends, and BC becomes 0. So set BC T3 equal to 0. Put T equal to T3 here. So this equation becomes 0 equal to minus I naught C T3, and this is T minus T2. Okay, T minus T2. So T3 minus T2 plus V in 1 minus cos omega naught T2 minus T1. So from here we can find this interval del T2, del T3, the time interval for which this mode 3 is being operated. है So at the end of this mode, now capacitor voltage has become 0 and inductor current has become 0. That was already 0. In fact, now it remains 0 till this point only. Okay. So now what will happen? You will see here. Uh, so this is the mode 3 we have already seen. Mode 4. Mode 4. At the end of mode 3, your capacitor was connected here. So what happened? This capacitor voltage has become now 0. This capacitor voltage has become 0. And now your diode, when you turn off the switch, then diode should get turned on. But diode could be turned on only when the voltage across this becomes positive, and due to capacitor it was not happening. Now at the end of mode T3, your capacitor voltage has become 0. So this diode becomes turned on. So now if you go waveform, if you see these waveforms, then this part up to here. This makes this part. This makes the this ZCS phenomena. Right after that, converter works normally. Now after this, your diode will turn on. Diode will turn on, and this diode will carry this I node. No current will be coming from this capacitor or this inductor. This diode will carry the current. It means your if you see your original buck converter circuit, then now it is current in the circuit is due to original buck converter, not due to L and C. L and C is the purpose of L was to connect in series with this switch was that we wanted this inductor current to make zero, so that after that it can be turned on. This capacitor voltage, this period, for which capacitor voltage remains positive, that period we want as minimum as possible, because this once this is zero, it is of no use, right? This is of no use. So um, that way this ZCS has been achieved in this particular converter. Okay, now the next step is that to get its voltage gain, right? So the voltage gain can be obtained by using this equation. If we can find, we know this voltage VC in different modes. Now we can take average of this, right? We can take average of this, and this will give us the voltage gain. So that is the one way of doing this. Another way is that another way of getting the voltage gain here is that we know that this is the ideal converter. So input power and output power both should be same. Input power and output power both should be same. So what we can do, we can find the input power and then make it to equivalent to output power. So what is the input power? Input power is E in I input, V input, right? So I input is the same current as inductor current, this inductor of resonant tank, and this I V in is constant. So we can take V into V out, V into V out, and we can integrate this 0 to TS, this IL, and we know that this was for 0 to T1 and T1 to T2, and rest of the time IL was 0. So these two equations are there. All the expression for IL are with us. So by putting those expressions and getting integration, we can find this expression. The energy is input from the source, and that depends upon these different time. This is T1, which is basically T1 minus 0. So del T1, del T2, and del T3, and all these expression we have obtained. So now next is output power. So what is the output power? Output power, we know that I naught V naught into dt, I naught V naught are constant. So this is I naught V naught into Ts. So this is output expression, right? So if we equate output, this is output energy expression. So we equate output energy and the input energy. As this is the ideal case, both should be equal. If we make it equal, then we get this expression for the voltage gain, right? You just substitute this value of del T1, del T2, del T3. If you put all the components, then finally we get this expression which relates the voltage gain V naught upon V in And this Q are, some variable which is defined to just R node upon Z node, normalized load. Then I node is the output current, and FNS is the normalized switching frequency. So remember here, one is two frequencies are there. One is FS, which is switching frequency, and another is F node, which is mm, resonant frequency 1 upon root LC. So anyone can answer which frequency should be more? F node should be more or FS should be more? Can you put your answer in chat box, please? बताइए. Let me know in chat box. Resonant frequency is more, should be more, or switching frequency should be more? There are 26 participants right now. अनुभव आप बताइए. Anyone can tell, please? शेयर कर रखा है. So definitely, you see here that this entire period is T, in which resonance is occurring for certain time only. So this is T is F, 1 upon F. So this T is, if I say this to be resonant T node, and this is TS. This T node is smaller than, very, very much small than TS, right? Switching period. So if I take this to be here, this is 1 upon TS, and this will be 1 upon T node. So 1 upon TS is what? F S, and this is F node. It means Fs is lesser than F node. It means Fs upon Fs upon F node should be lesser one. So Fs upon F node is FNS. FNS that should be less than 1. It means this value of FNS should be less than 1. All right. So this gives this. Right. Yes. This is the expression which gives the control characteristics curve of this voltage gain versus FNS for ZCS buck converter. So if you increase this normalized switching frequency, you can see it is between 0 to 1. You increase it, then what happens here? This M gain also increases. This is boost resonant converter ZCS. So our normal boost converter is this one. Let us quickly go through this. This is normal boost converter. Now I want to make it resonant converter, so I need to replace this switch. I need to replace this switch. So what I need to do? I need to connect one inductor in series with this, and then one capacitor. Right, so it is replaced like that. Now, as I said previously, that now diode is here, so I cannot assume to be constant current source. So I take these two branches here, C node and R node, and I represent it with V node. Remaining circuit is same, but input side V in is series with L in. So when this is the case, we can consider it to be a current, like a constant current source. Now the once this circuit is obtained, considering same assumptions, input current constant, load voltage fixed, right? We can easily simplify this circuit also, ZCS. Assuming initial conditions, what is happening in the circuits, and then previously only this inductor current keep on increasing, then this capacitor voltage keep on decreasing, like that we can achieve ZCS. At this point you can see ZCS when inductor current becomes zero, right? When inductor current becomes zero, then only this switch is turned off, so this ZCS is used here for turning off only. Now another is the ZVS topologies. So ZVS topologies are basically used for turning on the thyristor, for turn on. Z the ZVS is to turn on the SCR, right? So power switch is turned on at zero voltage. When the switch is off, a peak voltage will appear across it, causing the switch to be higher than in the hard switching. So how we do it? As we discussed earlier, this is L type switch, right? Here, this capacitor is connected across the switch. Then inductor is used for creating resonance in L type. In M type, this capacitor is directly connected across the switch and inductor is used for accomplishing the resonance in the circuit. If you want to make it unidirectional half wave operation, you just connect a diode here. If you want to make it bidirectional, a full wave operation, you connect a anti-parallel diode. So this switch will carry current in both the direction. Here switch will carry current in only one direction. Similarly here, right? So this now with these configurations, we can replace the switch. So this is a buck resonant ZVS. So in buck converter, this switch was there, right? This was the only switch, but here now it is replaced with this capacitor in parallel, and this inductor is being used just to create the resonance, and the remaining circuit is as it is. So we just transform this circuit into this simplified equivalent circuit, the for analysis purpose only, right? For analysis purpose. Now this is a buck converter, so this entire things can be written as I naught. Diode will remain as it is, this inductor will remain as it is, this side will remain as it is, this source will remain as it is. Now we starts again, it works in 4 modes. We starts it when let's say switch is your switch what is that? Okay, now at this point your switch is just made off. Now we are using the ZVS to turn on the device. When device is being turned on, we will use this ZVS. So let's say switch has become off now. Switch will become off. It means all the current will be carried through diode only, right? If switch has become off, then diode will be carrying all the current. Now this inductor current, now this inductor current, it will be carried through this capacitor, right? So this inductor current now will be inductor current will be decreasing, and this capacitor, which is this capacitor voltage will be increasing, then it start decreasing. But when it becomes zero, when this capacitor voltage becomes zero, because this capacitor is now directly connected to in parallel with the switch, so whatever voltage is across this capacitor, same voltage will be across this switch. Now when this switch becomes switch voltage becomes zero, then it will happen only when this capacitor voltage becomes 0. So at this point T2, this capacitor current becomes 0. Now at this point we can turn on the switch. Now switch is turned on, and it now remaining current, this current increases, and it becomes constant I node. And now when switch is turned on, then entire current is flowing through the switch itself, and which is basically inductor current. And in that case capacitor voltage remain 0. Okay, so in this way we see that because switch voltage has become 0, after then only switch current is increasing, so that will create 0 losses. Okay, so we stop over here. We have an afternoon. If we wish, we can discuss something about discontinuous mode of conduction that we have left before, and something about hardware also, how to design this current sensor, voltage sensors. So I stop here. If you have any questions, please ask. If there is any query, you can ask.
Shall I make them unmute?
Sorry.
सर उन टन्नीस को अनम्यूट कर दूं क्या, मतलब पैनलिस्ट बना दूं?
हाँ नहीं, जो पूछे उसी को बनाओ, सबको तो करो।
ठीक।
इसका कोई क्वेरी है अगर वो रिक्वेस्ट करते हैं तो कीजिए, नहीं अगर चैट बॉक्स में है तो फिर चैट बॉक्स से ले लेते हैं। कुछ क्वेरी है क्या चैट बॉक्स में?
चंद्रशेखर,
चैट बॉक्स में एक क्वेरी आया ना शायद कुछ। No sir, yes, what is the advantage of this converter? I told na that switching losses become 0 when turning on and turning off. At that time switching losses become 0 because once current becomes 0, then only the voltage across the switch will be built up, so power loss is 0. Similarly, if voltage becomes 0, then only current will start increasing when turning on, so now also power loss is 0. So that power loss was causing reduced efficiency, so this will happen. One is that. Another is this transition of increasing voltage due to, like here in second case, this capacitor, due to this capacitor which is in parallel with the switch. So the voltage across the capacitor cannot be suddenly decrease or increase. It will take, this capacitor has certain time constant, so it will take certain time, right? And because same voltage is appearing across switch, so this dB by dt of the switch will be taken care of. Similarly, in another version, the inductor is there in series, so that inductor current cannot be suddenly 0. It will take certain time, di by dt, it has certain di by dt. So that same current is being flown through the switch. So switch will also have low dB, di by dt. That's why the overall EMI, electromagnetic interference, that will be reduced.
Well, are there any chances that this type of converters are used in number of stages of building up the multi-level inverters? Okay.